All right. Hello, everyone. This is a report for our term project on machine learning course, COMP5212. Our group consists of 4 students, Liu Zhili, Yao Lewei, Xu Hao, and Yu Manli. And our project mainly focus on problem of image captioning. And we'll first investigate all the related works, and then we chose carefully to do experiment on the important ones. And finally, we propose our own methods to make an improvement. Part 1, we're gonna introduce a little bit on the research background of image captioning. First, what is image captioning? It is a progress of generating textual description of an image. For example, let's look at the left one. We can see a man playing guitar. The text we're gonna expect the model to generate is man in black shirt is playing guitar, just like that. It's the general idea of image captioning. So we can see that we're gonna use both NLP and computer vision to solve the problem. Next, I'm gonna go through all the important works to get a big picture of the image captioning area. The first deep learning work has been done in 2015, named Show and Tell. It combines the GoogleNet and the LSTM to generate a jointly training model to solve the problem. In the same year, attention mechanism has been introduced in this area. It proposed 2 different mechanisms, soft and hard attention. Soft attention just use softmax to compute attention, so we can use backpropagation on it. And hard attention use a stochastic progress to compute the distribution, the Gaussian distribution of the attention and then sample from it. In the next 2 years, adaptive attention and channel-wise attention has been introduced. Adaptive attention just use the attention when it is needed. And the channel-wise attention use more than one attention at one image to extract more data from image. And finally, we get the bottom-up and top-down attention. This one use fast RCN to perform object detection first and divide the image into K target areas, and then perform attention on the K target areas rather than perform on the whole image. It get a significantly better result compared to the previous work. So we're gonna do experiment to verify the result. And finally, we figured that transform do very well in the NLP area. So why not use transformer other than LSTM? So we're gonna perform the experiment on this one too. And you're gonna see the experiment result later on in this slides. In part 2, we're gonna detail exploration on all the key methods of image captioning and to get comprehensive understanding of the problem. First, I'm gonna introduce the general encoder-decoder framework for image captioning. The encoder is a method to extract the visual information from the image and then generate a latent feature. And then we feed the latent features into a decoder, act like a language generator to perform text generation. So we can use different encoders or decoders to do the job. And we will see that in the following content.
As Xu Hao has introduced, the general framework always input one single vector into decoder LSTM, which will lose many meaningful low-level features in the image and result in unsatisfactory results. Here, we have a try on one more famous method for captioning. It mainly focuses on output captions on different image regions at different time steps by attention mechanism. It is called show, attend, and tell. In general, it can also be divided into 2 parts. The first one is an image encoder, which transforms an image into its representation. Instead of getting one single vector, here a 2048 by 14 by 14 feature map is chosen for better captioning rich object information. The other one is the original LSTM decoder to decode image information into the text. Attention mechanism is put on the 14 by 14 feature map. It reweights the encoded image to tell the decoder which part should pay more attention to generate the next word. Here, soft attention is applied, which means you only need to learn weight, alpha I, ranging from 0 to 1 to put it on the feature map. The reweighted feature map, last output word, last hidden state in LSTM, is input to the decoder for generating the word. As you can see here, attention parts always put emphasis on meaningful and different part in the image. Later we will show the experiment on this method. However, when it comes to more complex image, this attention mechanism always fails to generate various captions. The main reason is that such kind of attention is still too coarse to catch many object relationships. Here is another baseline we have tried, called bottom-up and top-down attention. Instead of a single encoder with a single feature map output, here a detection method called faster RCNN is utilized to detect the objects in the image. Generally, faster RCNN has a RPN part. It uses anchor method and the regression to get the corresponding box of different objects in the image, called the proposal. The proposals are then fed to feature maps for ROI pooling and final bounding box regression. Finally, for each image, we will get n bounding box and their features through ROI extractors. In a word, faster RCNN acts as a hard attention mechanism to choose which feature decoder will use to generate text. The decoder constitutes of two LSTMs, one for attention, the other for language modeling. The first LSTM gets three inputs: the last hidden state, the mean of the proposals, the bar here, as you can see, and the last time step word embedding generated by the LSTM. It outputs the soft attention on VI. VI is the proposals given by the faster RCNN. Then these weighted proposals are fed into the second LSTM, just like the show, attend, and tell do. So we jump this introduction. However, since more powerful language models better than LSTM have already appeared, why not using them? Here, we propose to use Transformer as the language model instead of LSTM. As you can see, different from directly use LSTM as a decoder, we still encode and decode the feature proposed by faster RCNN. Here, 6 encoder and decoder layers, 8 attention head per layer, are applied in the transformer. We set the channel of V, K, and Q to be 64. This is our captioning model combined with faster RCNN and transformer. Later in the experiment, we will show that this method outperforms both two methods mentioned before.
Part 3. Experiment, verify, and explore on image caption. Dataset. The dataset we use is MS COCO. It contains 80 categories, thousands of images in training, validation, and testing. Each image is labeled by 5 captions. The some example listed here. For data pre-processing, we prepare the pre-extracted virtual features for all images. These features are treated with pre-trained encoders. There are 5 evaluation metrics used in the following experiments: Blue, Meteor, Roach, Exciter, Spice. The first 3 are designed for machine translation originally. Exciter and Spice are designed for image caption particularly. For all these metrics, the higher the value is, the better the performance is. I will introduce each briefly. Blue. Blue is based on n-gram precision in candidate translation from reference translation. n can be 1 to 4. Then compute the geometric average from the unigram to n-gram precision to get blue 1 to 4. The unigram is to measure the accuracy of word translation. Higher n-gram is to measure the fluence of the translated sentence. Material is based on n-gram precision and recall. It uses word lists to calculate the matches and chance to evaluate the sentence fluence. Routes is based on recall. To adapt it to image caption, use longest common subcolumns. Slider is a consensus-based image description evaluation. It introduced the term frequency, inverse document frequency, as a weight for the n-grams. They regard the sentence as documents. Then they calculate cosine similarities to measure the sentence consistency. The last one is SPICE. It's a semantic proportional image caption evaluation. It's based on words. It first transforms the calculated reference captions into sense graphs. They make the objectives, attributes, relations in these sense graphs to unigram, 2-gram, 3-grams, and calculate the precision recall to obtain F1 score. Then they get the semantic match qualities of the two sentences.
Here we show the experimental results of the introduced methods. The first one is the training result on soft attention. We use Adam optimizer as learned in the course and some other hyperparameters you can see here. One thing need to mention is that because one LSTM output a wrong word, the whole sequence easily failed and the training will not be stable. So here, teacher forcing is adopted. It means that at each time step, we only input the ground truth word into LSTM for generating the next word. We use BLEU4 as criterion to pick the best model. The whole training contains two stages. First, we fix the ImageNet trend encoder and only train the LSTM decoder. You can see the training loss and the validation loss decrease and converge to a small value. Validation BLEU4 increased gradually and we pick the best model when it reached the peak. For the next stage, we fine-tune the last two layers of the decoder, starting from the best model of stage 1. The training is not much stable, but you can see the downtrend of training and validation loss at first several epochs. We also choose the best model here for next experiment and visualization. Beam search is also used to enhance the model's performance. The idea is simple. Instead of only output one word from LSTM at each time step, which always result in failure captioning, we output n words. Here, for illustration, n equals to 2. At first time step, 2 words is chosen. At the next step, we combine 2 words and all words in the vocabulary and choose the top 2 sequence here, as you can see, A, B, and C, E, and repeat process. You can see the result of different beam size of our model, and when it's set to 3, model get the best performance. Here, we show some visualization of images. You can see here, the soft attention method can easily attend unmeaningful regions for LSTM word generation. You can see the last row of the image, the third word animal, and the attention mainly focused on the animal part. And for the last 2 word, it is the tree, so the attention mainly focused on the tree object. Next, we test the bottom-up and top-down attention with transformer. You can see some hyperparameters here. Here, schedule sampling is used instead of teacher forcing. It means that at first several training epochs, we use teacher forcing. And later, we close the teacher forcing and obey the original training method of transformer. Here, we use CIDER to pick the best model. You can see training loss and the validation loss in the first column. and they decrease gradually. And the next 4 figures for different matrices. The training is stable. Finally, we compare 3 methods. You can see our proposed method achieve higher score under most matrices except BLEU4, but is still close to the up-down results. Here is the visualization of our model with transformer. You can see when the image becomes more complex, the caption can also capture the most important part of the image and output reasonable captions. In conclusion, we have a simple taste in image captioning. The first one, we test the show attend and tell model. It is the first method to introduce attention mechanism, and it is good enough to be a baseline case. Second, we also use beam search to enhance our model. We found it can effectively improve the performance of show attend and tell. For bottom-up and top-down attention, it also introduced faster RCN for target detection and really enhanced the performance of captioning. We also propose another method based on transformer and faster RCN, which gets substantial improvement compared to bottom-up and top-down attention method as a baseline. Here is our references.